One of the many functions we perform here at the National Weather Service in Norman, Oklahoma are twice-a-day upper air balloon flights where we tie instrument packages to a balloon and send it up so we can determine the vertical structure of the atmosphere. This is performed twice a day here at Norman and at over 90 other locations across the National Weather Service nationwide, as well as 800 locations worldwide. By international agreement, the flight times are at 0Z and 12Z, which corresponds to midnight and noon in London, England. Here in the central part of the country, in the central time zone, our launch times are at 5 p.m. and 5 a.m. When we go to daylight time later in March, it'll shift to 6 and 6. The upper air flights that are performed by the National Weather Service and other weather entities worldwide are performed at 12Z and 0Z by international agreement, which is the time of noon and midnight in London, England. Here in the central part of the country, at the current time, our launch windows are at 5 p.m. and 5 a.m. When we go to daylight time later in March, it'll be an hour later at 6 and 6. We have a 90-minute launch window with which to prepare and launch our instruments and gather the data. We have the 90-minute window so that in case something happens to the balloon while it's in flight or something happens to the equipment, we have ample time to prepare and launch a second instrument and still get the data into the National Center for Environmental Protection in Silver Spring, Maryland, where the supercomputers reside. All the raw data is ingested, and then we can get the myriad of various forecast models that give us an idea of what the weather could do based on the data from the weather balloons, the radiosondes, and other surface-based weather measuring equipment. The need to measure the atmosphere in the vertical has been a recognized necessity for the better part of 200 years. The way that we do it now using a weather balloon and an instrument is basically unchanged since about 1938. The only thing that has changed has been the size of the instrument and the type of balloons that we used. Prior to 1938, we actually hired pilots who would load the various weather instruments into planes that would fly to certain elevations, take readings, and then fly to the next higher level. Unfortunately, at that time, pressurized cabins weren't plentiful with aircraft, so we were very limited in how high we could measure the atmosphere. Prior to that, we used kites that would be tethered at ground level with instruments that would be flown or tethered to the string at different levels. There was a brief attempt at using manned balloons, hot air balloons, back in the 19th century, but it was very hazardous for the individuals riding along with the instruments, and after numerous fatalities due to hypothermia and lack of oxygen, it was determined that a safer method was necessary. Right. The balloon is made of latex rubber, and to make it rise in the sky, we use a lighter than air gas, in this case helium. Most locations use hydrogen, and the Norman facility will soon convert to hydrogen very shortly. Now, I'm not going to put just a random amount of gas in the balloon. I'll actually put about 1,700 grams of helium in. The reason for that is we want to try to control the ascension rate of the balloon. The ideal number we're going for is 300 meters per minute, which is roughly 1,000 feet per minute. Now, as the instrument is being carried up by the balloon at that rate of 300 meters per minute, is taking a reading every second, measuring temperature, pressure, humidity, and wind speed, as I spoke of earlier. So that taking a reading every second, we're taking a measure of the atmosphere every 5 meters, which is roughly 16.5 feet. A typical flight lasts a little over 90 minutes. During that period of time, we'll take over 5,000 measurements of the atmosphere as the balloon takes the radiosonde high up in the atmosphere. Part of the preparation includes a flight training, which consists of a parachute, a length of string, and then the instrument itself. Eventually, the balloon will pop. A typical burst height is a little over 100,000 feet. The balloon literally explodes. There's a video available for viewing on YouTube where one of our weather balloons was tracked by a high-powered telescope it does literally explode and disintegrate. The parachute then opens, and the chute, string, and song gently fall back towards the ground. Now, one thing I'll want to do is get some distance between the radiosonde and the balloon. The ideal number I'm looking for is about 25 meters, or about 85 feet. The reason for that is when I first launch this balloon, it'll be approximately 4 feet in diameter. As the balloon ascends into the atmosphere, the air is thinner, and as a result, the balloon actually expands. By the time the balloon reaches that burst height of 100,000 feet, the balloon is actually almost 40 feet in diameter. Well, as this balloon is getting larger and larger, the skin of the balloon is actually being heated by the sun. As the balloon ascends, some of the heat from the skin of the sun is carried downward in the wake. And so the distance of 85 feet between the instrument and the balloon mitigates contamination of temperature data from this artificial heat coming off the surface of the balloon. Now, this balloon isn't fully inflated yet. My helium tank outside is about empty, so I have to go back outside, connect to a new tank. We can typically inflate 2.5 balloons with 1 bottle of helium. Once we switch to hydrogen, it'll be more economical. We'll be able to inflate as many as 4 balloons with 1 bottle of hydrogen. So the cost savings are significant. A length of string between the parachute and the balloon. Again, to keep a little distance from the parachute, we don't want the plastic edges of the balloon, plastic edges of the parachute cutting into the balloon skin. Now, the definition of a successful flight is 400 millibars, which is a little over 20,000 feet. That's fairly low compared to the typical burst height of 100,000 feet. Nevertheless, most of the atmosphere, troposphere, where the weather occurs, is in the lowest 35,000 feet above the surface. So we really strive to get accurate measurements at those levels. We launch twice a day, regardless of the weather. There's one exception where we will not do a balloon launch, and that is during a thunderstorm. The reason for that is twofold. The updrafts inside the thunderstorm can often be on the order of 100 miles per hour. There's no way to have a controlled ascent of this balloon inside the thunderstorm. The amount of wind shear and turbulence would rip the balloon apart. The other threat is lightning. I personally have launched in blizzard conditions. During the Christmas Eve blizzard of 2009, we had sustained winds of 60 miles per hour with sleet. Nevertheless, I did have a successful launch, and we were able to get quality data to get a better idea of the characteristics of that particular winter storm. Now, right now I'm just gathering up this 85 feet of string that I unraveled in a somewhat neat manner on this table, so that A, I don't trip over myself as I finish preparing for the flight, and 2, so it won't be tangled when I get ready to go out and do the actual launch. As I mentioned earlier, we typically do 2 flights a day. There are occasions where we'll do additional special flights. Oftentimes in the springtime, the Historic Protection Center will ask for a special flight during the noontime hour. So we can get a better idea of what changes have taken place with the atmosphere and whether or not the risk for severe weather is still as imminent as what we earlier thought based on the warning flight. We also do special flights for winter storms, trying to better determine where the rain, snow, freezing rain mix or transition zone may shift and change with time. On occasion, we'll also do one special flights in support of research projects, and we'll even do some in support of hurricanes, especially when there's a large hurricane in the Gulf of Mexico. The upper level data, the winds around 60,000 feet on up, is a useful tool for forecasters center to help predict the motion of the hurricane and changes in the atmosphere as the hurricane makes its way through the Gulf of Mexico. Well, much like a large circuit cube, it's actually a block of styrofoam. There is a particular reason why we use this, which I'll explain later when I bring the radiosonde out in preparation for launch. Now, the balloon is actually tied off to an inflation nozzle on the opposite end down on the floor is a counterweight, combination counterweight and switch, so that when the balloon has the 1,700 grams of helium in it, they'll actually lift the mechanism and cut off the gas. And at that point, I know the inflation process is complete. While the balloon finishes inflating, I'll go ahead and start prepping the radiosonde itself. It's a small device encased in styrofoam and cardboard that has the various instruments that I mentioned. The way it works is by way of a 6-volt battery, which I will charge and put into the instrument here a little bit later. Right now we're just getting the radiosonde out of its protective bag, and then we'll review the basic parts that actually take the measurements. The first thing I'll expose here is the thermistor. This is the device that actually measures the temperature. Voltage from the battery runs across the electrode on this thermistor. Changes in temperature alters the resistance of the electrical current, which is how it determines the actual temperature. Next is the measurement of the relative humidity, which is done by this device called a hygristor. It's a small piece of plastic that has rosin coated on it, similar to that used on a violin. Carbon particles are sprinkled on the rosin. That is then baked in place on the plastic. Rosin expands and contracts with changes in water vapor or humidity. That increases and decreases the distance between the carbon particles, which changes the electrical resistance, which is how it determines the relative humidity, based on that change in electrical resistance. As the balloon goes up and brings the radiosonde, the air that is sampled across the hygristor comes through an opening here at the top, across the hygristor, and exits out the bottom. I'll close this side seal so that it minimizes contamination of raindrops when it's going through a rain cloud or through a heavy layer of fog or drizzle. Now, with 90 of these being launched simultaneously across the country, we need to be able to track our particular instrument instead of one, say, being launched at Fort Worth, Texas, or Amarillo, Texas, or Little Rock, Arkansas. So to avoid the confusion, we have 4 frequencies that each office can use for tracking their particular instrument. To tune ours, all I have to do is cut these white wires. In other offices, they may cut the black wires, or they may cut both, or may cut neither. The next step is the most important step of all in preparation of these upper level flights. And that is to fill out and attach this sticker, denoting that this is a harmless weather instrument. Unfortunately, we have had more than one instance where one of our instruments was launched without this disclaimer. It landed at someone's yard. They mistook it for a bomb, called in the bomb squad, and caused a lot of unnecessary panic. I'll fill out where it was launched from, the date, and the time. Typically, the balloon will go up to about 100,000 feet over a 90-minute period, and then burst, parachute opens, instrument and parachute then descends and lands somewhere downwind. Usually that's on the order of 40 to 60 miles away, depending on how strong the winds are. During the summer, when the winds are lighter, we've actually had our instruments land within a couple of miles of the office. About 25 years ago, one of our instruments was found just southwest of Norman. It had been launched from Midland, Texas, 300 miles away. Now, if someone happens to come across one of these, they have an option. The label also talks about a shipping bag available on the side panel. And it looks like this. Someone finds the instrument, they can put it inside this bag, put it in the mail. It goes to our reconditioning center in Kansas City, Missouri. The instrument is refurbished and we can use it again. Below that is where the battery is stored. And at the appropriate time, we'll charge up the battery. Typically, we wait until 15 minutes before launch time because the battery only has a charge life of a little over 2 hours. And with a typical flight lasting up to 90 minutes, it doesn't give us a lot of room for error. So we typically wait until 15 till before we launch. It's now 15 minutes before launch time, so now we'll prepare the battery for initial charging. We use tap water. The battery is a very basic bimetal battery. It'll charge up to about 6 volts. Put it in water to activate. Let it sit in here for just over 2 minutes. Still waiting on the battery to finish its initial charging. Many times I'm asked, how much does it cost for one upper air flight? It's approximately $200. Now that sounds like a lot, but let's put it in perspective. The entire National Weather Service budget per year is just over $900 million. There are roughly 120 million taxpayers. Everything that the National Weather Service does, forecasts, warnings, measurements such as what we're preparing here, cost each taxpayer approximately $8 per year. Alright, the battery's gone through its initial charging, so we'll remove it from the water, shake off a little bit of the excess, but not completely drain it of water. Put it inside this protective bag that keeps the water from contaminating any of the instruments in the Radiosonde itself. I twist the batteries coming from the instrument itself 4 times counterclockwise. Why is that important? When I connect this battery, these wires, if they were left unwound, would act like an antenna, and there would be a small radio signal emanating from the battery through these wires that would interfere with the signal within the radio transmitter of the instrument itself. So by winding the wires like I've done, I mitigate the possibility of any interference. Now once I get this connected, I immediately lift this up off the solid surface. If I were to leave this on the solid surface like this table, some of the radio energy from the transmitter would be reflected back into the instrument and would damage it. Later, when we go in the inflation room to attach this to the balloon, I'll put it on the block of styrofoam, which has the same effect. It dampens the reflection of the radio energy back into the instrument. Now we need to wait a few more minutes for the battery to fully charge, which will take place in about 6 minutes. While the battery is charging, I'm going to test the pedestal, the tracking antenna upstairs inside the dome. And what I'll basically do is manually raise the antenna, and here it responds. It's up to about 45-degree elevation. And tell it to come back down. And we'll swing it to the left. And back to the right. This way I know I can intervene and control the antenna manually should the need arise. Now I'll park it at its default location, which is due north, at an elevation of 0 degrees. We're now ready to perform the most critical function of the preparation of the balloon flight with the instrument, and that's called baselining. What we're going to do is do a comparison of the pressure sensor from the radiosonde with a precision digital barometer, which is located approximately 1 foot away from the instrument. It is also positioned directly over a GPS signal, and we're going to do a side-by-side comparison of the latitude and longitude. The critical part about this is we need 5 uninterrupted minutes of GPS data before this can be considered a successful baseline. And the pressure sensor must be within 5 hectopascals or 5 millibars of the precision digital instrument. Process is now starting. Here's the readout of the pressure from the digital barometer, and this is the surface measurements from the instrumented tower immediately east of the inflation building. This is the latitude and longitude of the fixed position inside the shelter here that we'll be comparing with the readout from the radiosonde. Note here, here's the second by second readout of pressure from the instrument. Initial indications are that it is within 5 hectopascals. Here's my readout from the radiosonde, and I note there is 0 error, which is a good sign. I'll now denote that the baseline is begun, and we'll complete this in 6 minutes. Alright, battery is fully charged, the baseline is successful, so now we'll prepare to launch the instrument and the balloon. So I will securely tie the string to the slip ring on the top of the instrument. I've already called the local air traffic control tower at Max Westheimer Field. If an upper air site is within 5 miles of a controlled air tower at the airport, we give them a call, make sure it's okay to do a launch, so we don't have to worry about